I think I messed up. I didn't get 7.21.
Okay, do you just want to try it again?
Yeah. Okay, yeah, I got it.
Okay, awesome.
Oh, that's not wrong.
So when you lose this one, so it becomes H plus plus HCO3 minus. And if you lose another one, it becomes CO3 2 minus, right? This Ka is Ka of 1, and this is Ka of 2.
Mhm.
If you have 0.05 of these, 0 minus x plus x plus x. So it's 0.05, this is x and this is x, and then you just have to plug it in into that. X squared over 0.05. And then solve for x.
Okay. I got 2.2 times 10 to the negative 8th.
Well, am I doing something wrong? Hold on a second. 4.3 to negative 7 times 0.05 square root 12. I'm getting 1.5 times 10 to the 4. I got this. I'm gonna try it again.
All right. Because it's 4.3 times 10 to the negative 7th. And you just multiply it. Oh, I didn't square it. Oh, that's why. I didn't take the square root. I didn't take the square root.
Okay.
Yeah, I got 1.4. Yeah, that's what I got. That's tricky. He put that in there in case. Got to square it. Okay.
Then what is the pH after this much is added to this much? Okay. So let's find the moles of these first.
Okay.
Oh, it's the same. So there's no conjugate base that's being made. So then if pH is equal to pKa plus log this is 0.001.
I got 1.82.
Did you just do pKa?
Yes, the pKa.
I'm just wondering, why would they give you pKa and the concentrations of each one of these compounds, but they're equal to each other? And then you end up with a concentration of conjugate base. You know what I mean? You end up with a concentration of this.
Mm-hmm.
I mean, I get 1.82 if I just do this, but I don't think you should ignore this. But then this is 0. Down here it's 0. So I don't know how to do this one.
I can ask him about it.
Okay. But do you see my dilemma though?
Yeah, it doesn't really make sense.
Yeah, because from here you're gonna have to go one more. Like you're gonna have to go like that. 0.001. Oh, maybe that's what it is. Maybe that's what it is. Start out with that many moles, but then divided by total volume, which is 10 plus 10, which is 20 milliliters, 0.02 liters. That's 0.05 molarity, 0 minus x. And then I gotta find x. Ka2 is equal to x squared over 0.05, and then x is equal to, maybe that, yep. I get 4.25. I get 4.25. Does that make sense?
You just walk through it one more time.
Yes. So at first we did this and this, right? Acid and the base.
Yeah.
Well, they had the same number of moles, so they all completely disappeared. Create conjugate base, which was this, right? But this also can ionize into these, right?
Mm-hmm.
When they ionize, it's this. Does that make sense then?
Yeah.
Cool.
Okay.
If it's increasing pH, you need NaOH is going to be the strongest base, right?
Yeah. Oh, sorry, I scrolled down.
I'm so sorry. My mom's doctor is calling. Just give me 1 second.
Okay.
Hello. Yes, this is she. Hi. Sorry.
Oh, you're good.
Okay, so we want increasing pH. So NaOH is the most basic. So that's going to be the highest, right?
Mhm.
And then which one would give you the strongest acid?
HBr.
Good. This is strongest acid, so this is going to be the lowest. So I think we have that, and that. Now, can you see KBr?
Mhm.
Okay, KBr we have KOH and then HBr. It splits into those two, right?
Mhm.
KOH, is that a strong or weak base?
It's a strong base.
Good. What about HBr?
It's a strong acid.
Good. So if it's a strong base and a strong acid, and if they get together, it becomes neutral.
Mhm.
Okay, so that just turns 0. Not 0, that turns into 7, right?
Yeah.
So that should be in the middle,
Mhm.
right? Okay. And then we have NaCH3CO2. This is acetate. So this turns into NaOH and then HCO, right? So that's a strong base and that's a weak acid. So is the solution going to be acidic or basic?
Acidic. No, sorry, basic.
Basic.
I was thinking basic and I said acidic.
So is that going to be greater pH than KBr or lower pH than KBr?
It's going to be a greater pH.
Good. Going to be greater pH than KBr. So we need to say HBr something, KBr, NaC2H3O2, and then NaOH, right?
Mhm.
And obviously this is going to be NH4Br, but let's look at NH4Br. If you split it, this turns into NH3, and then this turns into HBr, and that's a weak base, and that's a strong acid, right?
Yeah.
So if you mix the two, you end up getting acidic or basic.
Acidic.
Good. So if it's acidic, it's going to have to be closer to HBr, which is a lower pH.
Okay. So it'd be this one.
Yeah. Okay, weak base ionizes in water. So let's forget about the water part and let's just look at this. This is 0.15000. And if 2.5% ionizes, what's 2.5% of 0.15?
1.5
Yeah,
or 0.15. Sorry, 0.15.
0.15, yeah.
Um,
That's 0.00375.
mhm.
Creating 0.00375, 0.00375. So you end up with this much OH minus, right? So can I find POH? I get 2.43. Can I find pH then?
Okay.
Okay.
So that's those problems. I don't think I can look ahead at the next ones. Let me see if it'll let me. What's this on? It's on. Okay, so the next one's on titrations,
Okay.
intermolecular forces. I don't think it'll. Oh, it will let me look at it. We haven't.
A
We
lot
haven't.
of questions.
Yeah, we went from 10 questions back over to 25. We haven't gone over any intermolecular forces or titrations yet. Let me see when we're doing them. Yeah, I think we're doing these after Thanksgiving. They don't have dates on them.
Okay.
Because we're finishing up with buffers tomorrow. Oh, one of the videos just disappeared.
Do you want to try the titrations?
Sure. I don't know where to start because we haven't gone over them, but.
Okay. Or I have some other questions that we can do, but I wanted to go over some content first, just so that I can kind of, you can kind of understand what is happening. So here. So before we do this particular question, let me just explain to you what titration is and stuff like that. Okay. But earlier we kind of talked about buffers, right? So I'm going to draw my buffer again. And buffers are usually made out of weak bases and its conjugate base, or a weak acid and its conjugate base, right?
Yeah.
Okay. So right now I have a weak acid. And basically I am going to titrate it out with a strong base. Okay. So here, this is 14. Okay. This is a titration curve. And if you look at a titration curve, the point where, remember inflection point, the point where the slope changes? Okay. The point where the slope changes is going to be called the equivalence point. Okay. Equivalence point means when the concentration of protons equals the concentrations of the hydroxide. So when acid equals base. Now let's just say that's like at 20 milliliter titration volume. Okay. Half of that is this, which is 10 milliliters, right? If it's 10 milliliters, this is going to be the mid-equivalence point, right? Mid-equivalence point means when acid equals its conjugate base concentration. So look at it like this. We are halfway there. Do you see how we are halfway there? That's this. Okay, when I titrate it completely, right, and OH minus is equal to concentration of H pluses, that's this. If I add an extra OH minus, this OH minus is going to now pair up with an indicator. When it pairs up with an indicator, it will change color. Okay, and that is this point right there, and that's called the end point. Okay.
Okay.
Now, what this is saying is at mid-equivalence, pH equals pKa, because the log of conjugate base over acid, it cancels each other out. That cancels out, so pH equals pKa at mid-equivalence. Okay. Basically it for this Henderson-Hasselbalch equation and the sigmoidal curve. Now, when you have two points like this, two equivalences like that here, when you have one equivalence here and then another one there, it means that this is a polyprotic compound. It means that you have at least two protons that are falling out. Does that make sense?
Mm-hmm.
Okay. All right, so which point A through D represents pKa of A?
Is it B?
Yeah.
Okay.
Good. Buffer region is indicated by which point? Ah, the buffer region, the mid-equivalence point, plus or minus 1 pH is the best buffer. Okay. So diprotic with NaOH, buffer region is indicated by which point?
C?
It's A and C.
A and C. Okay.
Yeah. What about intermolecular forces? How comfortable are you with it?
Not very comfortable. We haven't gone over it.
Okay, then let's just skip that for today.
Okay.
Okay, so this one, I'm just going to quickly show you. If I start out with a strong acid and a strong base, my equivalence point is 7. Okay, strong acid and strong base, all right? But if I start out with strong acid and I use a weak base, my equivalence point is going to be less than 7. Do you see? Because your final solution is going to be slightly acidic.
Yeah.
If you start out with a weak acid and add a very strong base, it's going to look like that. So weak acid and a strong base. Your equivalence point is going to be higher than 7. Okay. But if you start out with a weak acid and put a weak base, it's going to look like this. And your equivalence point is going to be 7. Does that make sense?
Yeah.
Okay. So if you have, if you have a weak acid and a strong base, your solution,
it'll be less than. It'll be less than.
it'll be basic.
Oh, it'll be basic. So pH greater than 7.
Yes.
Okay. Oh.
And which one of these will be acidic solution? If you want acidic, you want strong acid and weak base.
So HCl is a strong acid.
Mm-hmm. But so is HBr.
Yeah. KOH is a strong base.
Mm-hmm.
Would it just be that? Would it just be this first one?
Yes.
Okay.
So there's one which is 50 milliliters and the other one, oh, this is low concentration and this is, oh wait, what? What's the difference? Oh, this is supposed to be the same thing.
So the buffer region would be like A. Would it be like A or B, or is it one or the other? Because they look very similar.
Mm-hmm. I think it would be A.
Okay.
Results in basic solution at the equivalence. If it's a basic solution, it means that we need a strong base, right?
Yeah. Would it? Okay, so it's not gonna be. It's not gonna be B.
Yeah, it's not.
HCl. Isn't HI strong acid too?
It's a strong acid, yeah.
So it's not gonna be B or D.
Mm-hmm.
So I'm thinking. I can't remember if potassium or sodium makes it a stronger base.
Potassium, it's the first column of the periodic table. So usually first column of the periodic table are very strong.
So it would. Sorry, it would be potassium.
Potassium is a, yep, potassium
Okay.
is a very strong base.
Okay. And then this is intermolecular forces. For formic acid.
So weak acid and a strong base. Formic acid is COH2. Formic
Okay.
acid is either way a weak acid.
Oh, so it's a weak acid and a strong base.
So it's 25 milliliters. And then I have NaOH, 29.80 milliliters, 0.0567 molarity. And that's the Ka of formic acid. At equivalence, we need the molarity of this. And 67.58 molarity.
That's
So
what I got.
H plus COH minus, that's 67.5800 minus X plus X plus X. That's Ka is equal to X squared over 67.58 and X is equal to 0.95. I don't think that's right. I think something's wrong with this.
Is it supposed to be just a decimal? Like,
I think so. I think I just did it wrong. Yeah. This was 0.06758. This is 0.0658. I get 2.45.
yeah, that's what I got.
Okay. Lindsay. Try doing some more. I won't see you till Saturday, right?
Mm-hmm.
Okay. Try doing.
Are you still able to meet Saturday afternoon?
Yeah.
At what time do you normally?
Afternoon. Oh.
Or
Would you maybe possibly be able to meet up a little bit earlier on Saturday?
mm-hmm.
Yeah.
Yeah. What time? What time works for you?
Hold on a second. I have to do the conversion. Give me one second. I'm now in California, and so my times are all like all messed up. Would 11 a.m. be okay for you?
Mm-hmm. I think so. Yeah.
Okay. So let's move your 1 o'clock to 11 a.m. to 12:30. Okay. Sounds good. Then I will see you on Saturday.
Thank you.
Okay. All right. Have
See
a
you then.
good night. I'll see you on Saturday.
All right.
Okay.
Bye.
Bye.